is an inducible control. The item associated with genes turns the genes off. Whereas in repressible, the material associated with the genes turns the genes off. All right, questions about that? Anything about that that needs clarity? Put it back together again, and that's what the ligase does. DNA polymerase, which does what DNA always does, it adds bases to a growing chain of DNA. Restriction enzyme cuts DNA in the middle of palindrome. So for example, if we had a cat-tac palindrome, it cuts the DNA in between the two T's. Well, what we then do is once we've cut your DNA, think about it. Do you have the same sequence of A's and T's and G's and C's as the person next to you?
No.
No. So if I cut your DNA, for example, if I cut your DNA and I cut your DNA with the same enzyme, I'm going to get different sized pieces. We can then put that DNA in a gel that looks almost like extra thick gel. And that gel will move. We then send an electric charge through the gel. It's going to cause the DNA to move. Small pieces move faster than big pieces do. So then we wind up with a band that you've all seen now on the TV shows, all those little lines of DNA. We can then match DNA samples and determine lots of things. We can determine paternity, we can determine crime scene issues, et cetera, et cetera. Electrophoresis has been a big boom for DNA fingerprinting. For law enforcement, it's also been a big drag on resources. Because now everybody wants to run DNA on everything, rather than just doing police work and finding it out the old-fashioned way. But it gives us great abilities. Another thing we can have are probes or hybridization. DNA probes involve making a piece of DNA that's complementary to the gene we're looking for. For example, if I want to know, suppose you're a woman and you want to know if you have BRCA1 or BRCA2. Those are two genes that we know increase a woman's likelihood of having breast cancer. Well, we can take your DNA and take a probe. What the probe is it's either a radiologically labeled or a fluorescently labeled. We can make them either so they're radioactive or they glow in the dark. We can take some of your DNA, we mix your DNA with that probe, and if you have that gene, the probe's going to stick to it because it's going to be complementary. We can then look at the results and see if you carry that trait. And that allows us to know, is a gene present, is a gene not present. A little bit farther away from the gene we want, because you don't want to cut the gene you're trying to work with. You also cut a plasmid, that's going to open it up. We create these sticky ends. What I mean by that is if this is cut with a poly-A enzyme, so there's lots of A's at the end, guess where we want to cut this one? With lots and lots of T's, so hopefully they'll stick together like we want them to. This is our ideal, this is what we want, but we get all three. We get plasmids stuck together, we get DNA stuck together, and we get what we want. That's where this antibiotic resistance comes in. Because if we make sure we have a plasmid that has antibiotic resistance, we can then grow all of this out on antibiotic plates, and the only one that will grow is the one that has the antibiotic resistance. This one will grow, but it won't express the genes we're looking for. This one won't grow at all because it'll be dead. This one will grow and express the genes we're looking for. So that's how we would then isolate that bacteria. When we do the glow in the dark lab, that's how you find the bacteria you're looking for, because only one of the plates you make is going to have bacteria growing on it and have those plates glow in the dark. Then you know what you want, you can isolate those and then grow them as much as you want.